In this video, we will talk about the number of nuclei left after a radioactive decay. Suppose initially we have n0 number of nuclei, n0, that is at t equal to 0 seconds. And after some time, let n be the number of nuclei left, that is at time equal to, let's say, some t itself. Now we have number of decayed nucleus or decayed nuclei is equal to the final number of nuclei, that is n minus n0, or we can take that as delta n. And we have the number of undecayed nuclei. What is the number of undecayed nuclei? This one is the n is the number of undecayed nuclei. And according to the law of radioactivity or law of radioactive decay, we have the rate of disintegration of the radioactive number of nuclei, that is delta n by delta t. Delta t means the final time minus the initial time. That is delta n by delta t is proportional to the number of nuclei left, that is this n. So this is the law of radioactive decay, and we have to assign a negative sign in order to balance the equation. That is, initially, for example, initially we have 100 number of nuclei, and after some time it turns to 70. So what is the value of delta n? Delta n should be final minus initial, that is 70 minus 100. So this will be minus 30. So to keep the equation positive, you have to assign a negative sign. That's why we use a negative sign. Okay. Now, let me erase this. Now what happens when delta t tends to 0? When delta t tends to 0, this can be written as minus dn by dt. This is the limiting case proportional to n. You can remove this proportionality by multiplying with a constant, that is dn by dt is equal to some lambda into n. This lambda is called the decay constant. Decay constant, or some authors may say that as disintegration constant. Okay, decay constant. Now we have dn minus dn. I can take this n to the left and this dt to the right is equal to lambda t dt. It's better you write this negative here. So dn by n is equal to minus lambda dt. Now in order to remove this d, I'm integrating both the sides. Okay, so here we can write dn by n is equal to, since minus lambda is a constant, I can take that out, minus lambda into integral of dt. This will be, we know integral dx by x is equal to log x to the base e. So this will be log n to the base e is equal to minus lambda into integral dt is t, and we have to assign a constant of integration. So this equation will become log en is equal to minus lambda t plus c. Now we need to find the value, or let me write it here, log en is equal to minus lambda t plus c. Now we need to find the value of this c. For that, we can take the initial condition. That is, when t equal to 0, we have n equal to n0. That is, n equal to n0 when when t is equal to 0. So this, I can substitute these values in this equation. So log e n0 is equal to lambda into, when n equal to n0, we have, this is e, right? Okay. We have t equal to 0. So lambda into 0 plus c. So I'll get log e n0 equal to c. Now substitute this equation again in this equation. Okay. So we have log en is equal to minus lambda t. Now we have c is equal to log e n0. Log e n0. And if I take this log e n0 to the left, I'll get log e n minus log e n0 is equal to minus lambda t. And by the property of log, we have log a minus log b equal to log e n by n0 is equal to minus lambda t. Now if log to the base e of a is b, I can write this a as e raised to b. Okay. And if I use this equation in here, this n by n0 stands for a. So n by n0 is equal to, here b is this whole term is b. So e raised to minus lambda t. And the final expression is equal to n equal to n0 times e raised to minus lambda t. So this will be the number of nuclei after a time t. Now we have to derive an expression for the half-life of a radioactive substance, usually represented by T half. T half basically means, by the definition, when the number of nuclei turns to n0 by 2, that is half of its initial value, that time when this happens, that is n turns to n0, then we call that as T equal to T half. For example, we have initially 100 number of nuclei, that is at t equal to 0 second. Now after some time, let's say we have 50 number of nuclei after, let's say, some 12 seconds. So this 12 seconds is the half-life of this radioactive substance. So when n turns to n0 by 2, that time is called the half-life. So we have the expression n equal to n0 e raised to minus lambda t. Now I can replace this n with n0. So n0 by 2. So n0 by 2 equal to n0 e raised to minus lambda t. T becomes t half. Okay. N equal to n0, t equal to t half. I can cancel this n0. So we'll get half is equal to e raised to minus lambda t half. Now taking the reciprocals on both sides, we have the reciprocal of 1 by 2 is 2. 2 equal to 1 by e raised to minus lambda t half. This will be 2 equal to this negative will get removed when we take this value to the numerator. So lambda t half. Or I can write e raised to lambda t half is equal to 2. Now take the log on both sides. Log e raised to lambda t half, log to the base e, okay, equal to log e2, log to the base e. Now we have log e raised to x to the base e is actually x. Using this equation in here, this identity in here, we have lambda t half instead of x. So this will get removed. we usually use the log of 10, log to the base 10. So in order to convert this natural log, that is log to the base e to log to the base 10, we have to see this will be lambda t raised to 1 by 2 equal to, in order to change this one to the base 10, we have to multiply with 2.303. Now the base can be changed to 10. So this will be lambda t half is equal to 2.303, and we know log to the base 2 is actually 0.3010. So lambda t half is equal to, this will be approximately 0.693. So we have t half is equal to, taking this lambda to the right, we have 0.693 by the lambda. That's lambda is actually decay constant. So from this expression itself, you can see that there is no n0 in here or n in here. That is, this n is absent in this equation. That means half-life doesn't depend on the initial value of the nuclei. Clear?